In this video, I'm going to be showing you how to use Autodesk Fusion 360 to calculate a structural analysis for a truss. This is for a project that we're doing in technology teacher education at the BC Institute of Technology, and the students have to design a truss that is supported at 2 nodes and holds a 2 kilogram weight, 20 newtons of force, at the 3rd node for 30 seconds. The idea is to build the truss as light as possible, given certain constraints. The current method of analysis is to use hand truss calculations and software known as JF Matrix, a website that offers a number of forms of structural analysis, particularly truss analysis. And JF Matrix allows you to go through and analyze trusses and see the results, stresses and strains. It's important to know how to use both hand analysis and traditional truss analysis before you move on to using Fusion 360 or other finite element analysis methods. To use an analogy, calculators are really great if you know how to do math already. But if you don't know what math is and you type 3 plus 3 into your calculator and you get an answer of 9, you'll carry on with your calculation thinking that 9 is the right answer and not go, maybe I pressed the multiply key instead of the plus key. So it's really important that you understand the basics and that you're able to visualize where tensile members will be, where compressive members will be, and how changing the position of a node is going to affect the forces in those truss within the truss. So it's very important that you have a basic understanding of trusses before you move on to do any more complex analysis. But if you're ready for the complex analysis, oh man, do you get pretty pictures. And can you ever do really neat things when you start looking at your truss in 3 dimensions. I'm going to be showing you how to solve these trusses using Autodesk's Fusion 360. If you don't have Fusion 360 installed on your software and you happen to be a student and have access to an educational email address, you can create an account with students.autodesk.com and you can download free software from Autodesk. They make using Fusion 360 really easy. It's almost like they want to get you hooked on it. Once you have Fusion 360 installed, you'll have to log in with your Autodesk user ID. Fusion 360 is a cloud product, which means that we're going to use some of Autodesk servers to store files and process some of our analysis for us. Fusion 360 is a 3D parametric program, which means that just like Inventor and SolidWorks and a number of other programs, we can develop 3D objects, but it also means that to do that, we're going to need to start in 2D sketch mode. So to start, what we're going to do is we're just going to come in here and we are going to tell it we want to create a sketch. And so you can just click on the down arrow under sketch and tell it create sketch. Now the first question it's going to have is which plane do we want to create the sketch on? There's 3 planes, obviously, 1 for each axis, and we'll choose this one. It really doesn't matter. So there we go. We've got a 2-dimensional plane now, and we can create 2-dimensional drawings on this surface. And we're going to start by creating some construction lines to hold on to our truss. So you should have a sketch palette that's opened up on this side of the screen. And if that hasn't opened for you, you might have to just do a quick Google search on how to get the sketch palette to open, because what we're looking for are the construction lines. So step 1 is to turn on construction lines. And the construction lines are going to be tools that we use for setting the parameters and measurements. We're going to be able to edit them later on, but they'll be invisible in the final product. When you create a drawing in parametric CAD software, you're basically programming the drawing. So what we're going to do is we're going to start with our construction lines, and we're going to come in here and we're going to go sketch, and the drop-down menu gives us a line. We could just tap L, but here we go. L for line. And we're going to assume that this is our middle node of the ones that were required. So we'll have an end node out here somewhere. Don't worry about how far out you put it. Just somewhere that looks good right there. We'll come into the middle right there. And then we'll come out to the end right here. We'll have a support node here. We'll have our top node here. And then we'll come down and we'll close off our truss right over there. We'll also have a vertical support coming up right here. And then a couple of zero force members, the members that are holding our support nodes in place, one to right there, and one up to right there. And that gives us the basics for our truss. Now you can create a more complex or fancier truss. I'm just sticking to something really simple to keep the demonstration down to a fairly short timeline. Now we can come in here and turn our construction lines off. We're not going to need them anymore. Now, what we're going to do is, remember, we didn't pay any attention to dimensions when we were putting this in, and that's one of the beauties of parametric CAD software, is instead of the dimension showing you what you drew, the dimension controls your drawing. And you need to add some constraints so that it understands what you're telling it what to do, but we'll show you in just a minute why that's really cool. To add a dimension, you press the D key. It's right down here, sketch dimension. And so I want to dimension from this point right here. You can see the little dot appears right there to that point right there. And you can see right now I drew it to be 75, but I'm just going to click right there. I want my dimension line to appear right here. And I'm going to tell that I want that to be 150 millimeters, because that's our design parameter. And now, bang, you can see that has changed that dimension out to 150 millimeters. And from that first node out to this end node right here, that is going to be 400 millimeters. So it's not 400 right there. I'm going to type in 400 right now, and that becomes 400. Got a couple other nodes that I want to dimension right here, from right here to the bottom right there. We'll set that out to be, somewhere around 200 for now. And that's looking a little bit ugly, but hang with me. This node right here to that node right there. You have to drag it down here so that we actually get don't get the aligned dimension. And let's move that out to 210. And then we need drop down too low. Just a minute right here. Let's hit escape to get out of sketch dimension. And let's just drag that back up. We can drag that dimension back down where we can see it right there. And then let's press D to add a dimension in here, and we'll dimension from that line. This will be a vertical dimension to that line right there. We'll come in and we'll put it right here. And that's aligning. We don't want that. Just undo that. We don't want that constraint in right there. We need to bring this node up a little bit more. There we go. You can drag these nodes around again, because until we give them dimensions, they're not constrained. So we'll hit D, dimension right there, dimension right there. From there to there, and drag it out far enough so that it's off the drawing and isn't an aligned dimension. And now we can tell it, let's make that 60. There we go. And then in here, we'll take this dimension and that dimension, and we'll bring that one up there. We'll make that 80. So we've got a truss that's 80 millimeters high. That node's going to be at the 60 millimeter mark. And one final dimension, we want to know the distance from right here to right there. And we'll make that 170. Now, what's really cool about doing this, and before I go on and talk too much about that, you've got some commands right down here on the bottom middle of your screen, and you've got zoom to window, and you can also set it to be zoom to fit just by telling it what you want it to do, and that'll fit everything onto the screen. And if you want to shrink the sketch palette up because we don't need it right away, just shrink that and drag that off to the side. And now you've got a window looking something like this. And this has all the dimensions for our fairly simple truss in here. Now, what's really cool about this is that in parametric CAD software, you can come along to any one of these dimensions, double click on it, and I want a higher truss now. I'm going to move that up to 120. And now you can see that the dimensions of the truss have changed. And all my lines have followed those changes in dimension. What's really cool now is that we can use our construction lines as the basis for the nodes of our truss. And we're going to start doing that by creating some circles where we want the nodes to go. And we're doing this to match the specifications laid out in the design challenge. And to do this, we're going to sketch some circles. And C is your command for a center diameter circle. So we'll just click on C, or we'll select center diameter circle. And right here is one of our support points. And there is a 30 millimeter diameter circle right in here. So now I can stretch that out to whatever size I want, but you can see that there's a size box in there. I'm just going to type 30 and press enter. And I've got a 30 millimeter diameter circle right there. Now there is a space for a support in there. And so I'm going to click on that center point again. Right click brings up this little menu right here. And I can repeat center diameter circle, or I could just press C. And now this is going to be a 12.5 millimeter diameter hole. And we're going to want to cut that out later on. So we're just going to create that hole right there. Now, right now it's not a hole, but it will be when we go to extrude it later on. Again, to recenter the screen and zoom in, I'm just going to use fit right here, and then I'm going to zoom in on this side of the screen to create another circle down here. Right click. No, I don't want it to repeat fit. Let's cancel that. Press the C key for center diameter circle. And again, 30 millimeters. And repeat center diameter circle, 12.5 millimeters. And that was 2 hits of the enter key. We've got a pan key right down here in the middle of the screen. That's our hand for moving this around. And that lets us zoom in right out here at the end where we have our load. To get rid of the pan, just click on the screen and then C for center diameter circle and a 30 millimeter diameter circle and C a 12.5 millimeter diameter circle right in there. I'm not too worried about where those dimension locations are going, and I'll fit that back onto the screen. So those are our primary nodes where the one support is, the other support's going to be here, and our load's going to be out here. We're also going to have some nodes for reducing the length of our compressive sections. And because of the rules of this project, everything has to be a fully constrained, statically stable truss. So we have to put some nodes right here, and right here. And those nodes can be any size you want, up to 20 millimeters in diameter. So let's put in some 20 millimeter diameter nodes there. So again, press C for circle, and just tell it we want a 20 millimeter diameter node. And we've got a circle right there. C for circle, pick that point, and 20 millimeters diameter right there. And C for circle, 20 millimeters diameter right there. Now again, the really cool thing about having made this parametrically is that now when I come along and I change some of these parametric dimensions, for instance, the 60 millimeters right here, if I change that up to 70, pop, the node moves along with it. And if I want to move it out a little bit further, I can come down here and I can change it to 220 and it moves out that way. So you can come back and edit your truss very easily based on your sketch just by typing in the dimensions. That's going to be very powerful once we get to the modeling and we're trying to optimize our size. So it's a little bit more complex to start your drawing than AutoCAD, but once you get going, it pays back in spades. It's really awesome to work in a parametric environment. Now we're going to need to create the actual truss members. And for creating the actual truss members, we're also going to be creating some lines, but what we're going to be doing is we're going to be offsetting our construction lines. So in Sketch right here, you'll see that we can come down here and pull up an offset command. And when you go to offset, you'll notice the offset window pops up over here and it says chain selection. We don't want to do that. Chain selection means that when you go to do your offset, it's going to go about and find anything that's linked up to it. And we don't want that. I'm just going to cancel that for a second. O for offset again, and turn off chain selection. And just pick a member right in here. This is going to be in tension, so it's going to be fairly narrow. So I'm fine with a 1 millimeter offset right there. Okay, and there you can see our 1 millimeter dimension. I just zoomed in there a bit. And you can right click and say repeat offset and take that construction line. But this time, flip the dimension over that way. And now you should have 1 millimeter offsets on each side of that construction line. And click OK right there. There we go. Nice. The pan hand is right down here, so you can come and take a look at your next member you want to work on. And we'll do the same thing again. You can press the O key for offset and click the curve you want. There we go. We put one on that side. We say OK. And O for offset. Click that curve and flip it on the other side. And we're OK. Remember to flip it. It's the flip button over here on the offset window. And now we've got a couple of truss members coming up and down right in there. Our zero force members are also going to be fairly lightweight. We don't need to put a lot of force into them. So let's do them right now. We'll just click right there. There we go. We've got one offset done. And O for offset right in here. And same thing, we're going to click that member and we're just going to flip the side of it. Okay, now the bottom member, oh, we'll finish this one off because this is a zero force member. It's just holding those nodes steady. And offset, O for offset, and 1 millimeter should be fine. And O for offset, flip the side over, 1 millimeter is fine. We're going to come down right here. Now, these members on the bottom are going to be in compressive stress, so they're going to need to have a bit of meat to them. We're going to make them a little bit thicker, and we'll go O for offset, and this time we'll pick this side right there, but we'll tell it we want that to be offset 3 millimeters that way, O for offset, and we'll flip the direction, and 3 millimeters that way. And that comes through right in there. And let's see right here. Let's zoom to the whole thing. I wanted that to, oh, there we go. There's our zoom to fit. Okay, this one coming up and down here is probably going to be under some of our heaviest compressive load, and it's a fairly long member, so O for offset, and we'll set that up to 4 millimeters. Our maximum member width is 8 millimeters, so 4 millimeters to each side really maxes that out for us. O for offset, click right there, flip the direction, and set it to 4 millimeters on that side. and we'll finish up with a fairly narrow section here at the back. This one does get quite a bit of tensile force in it, so let's maybe give it a 2mm offset, and we'll do that again right there. O for offset, flip the direction, 2mm, and down here we'll make it 3 just to keep in with everything else that we've got going along the bottom. And for offset right there, flip that direction around, and all right. Now we have a truss that is set up here, and we can fit it into our window nicely and take a look at it. And what's really cool about this is we're going to take this truss and extrude it. And in the extrusion process, we're going to make it into a full 3-dimensional truss, the width that we want. Before we do that, I'm going to do one more thing, and this doesn't exist in the real truss, but right down at this end, we're going to be applying a vertical load into here, and it would be really nice to have a vertical surface in here to do that. So what I'm going to do is I'm going to do one more offset, and I'm going to offset this line right here in the other direction, and I'm going to offset it 6mm, so it comes right down to here, and you can see that's just going to give me a flat surface right on the very bottom right there, and that's going to be our bearing surface for our load. It's a little bit of a cheat, but sometimes putting cheats in to help with your analysis pays off down the road. So I'm just going to click OK right now, and that doesn't quite go all the way through. I'd like it to go all the way through to this side, and so just as an AutoCAD, you've got the extend command. We have an extend command right here, and it's pretty smart. If I come down here and click on that, that extends it through right to that intersection right there. There's also trim commands, but what's kind of cool is that you don't need to use the trim command just yet, because when we do our extrude, a lot of that will take care of itself. Now, once again, you want to check and make sure this is all working okay. For instance, try changing this dimension right here. You might have to hit escape to get out of a previous command. Then let's double click on our 200 dimension right there. And if I bring that back to 180, that node changes position. And you can see that as we change our node position, the members all shift and move around to match up with that. And what's going to be really cool is if we do our extrusion right, that's going to happen even after we do our extrude. So we've got the truss modeled in 2 dimensions. Let's start making it 3-dimensional. And so I'm going to stop sketch right now, and that will kick us back into a 3-dimensional state. And from 3 dimensions, you've got control of how you view your truss right here. And so now you can see we're looking down at it from this side. And what we're going to do is we are going to create by doing an extrude. So this is a fairly standard process in 3D modeling programs, as you create a 2-dimensional outline, and then you go ahead and you extrude it. Now we have to choose what we want to extrude and how far we're going to extrude it. But let's just come in right here. And if I click on that surface, you can see I don't want the middle coming along. I do want that tiny flat bit to come along as part of my extrude. And all of that circle right in there, but not the middle circle. We don't want that getting extruded. Down here, we want that member to get extruded. That member to get extruded. There we go. We've got the circles getting extruded. I'm just going to hit the fit button to bring that back into view so I can see I want everything coming along right in here. Watch for those little pieces and make sure you don't miss them. Okay, that's going to extrude all of that. That member will extrude, that member will extrude, and that member will extrude. Up top here, we'll extrude that member, that member where it comes through in there. And there we go. That member and that member are going to get extruded. Use the fit button to resume. Coming down here, we'll extrude that, that section, that section. Oh, there's a tiny little piece that we don't want to miss. And let's fit this together. And we've got that all selected. Looking at that, everything looks really good there. And now we just need to tell it how far we want to extrude it. Now, this distance is, again, it's a parameter, and you can change it. Things to think about is that the MDF itself is 3 millimeters thick. So you're going to have two layers at 3 millimeters thick, and then whatever gap you want between them. We're going to create the gap in just a minute, but I'm going to go with a 20 millimeter gap. So that means I'm going to have 20 millimeters plus 3 millimeters of MDF on one side plus 3 millimeters of MDF on the other. So I'm going to do a 26 millimeter extrusion right here. And there we go. We now have the beginnings of our truss sitting there in 3 dimensions. And I can do this nifty little spin thing to look at it because I've got a really cool 3-dimensional mouse that we don't have as standard on our lab computers. Okay, so there we go. We've got the basics of our truss. Now, obviously, our truss is made out of 3 millimeter strips of MDF. So I've got to get rid of all this material in the middle. Well, we're going to do that by creating a negative extrude, and we're going to make all the material in the middle disappear. And to do that, we're going to start by creating a new sketch. And if we look down at the bottom of our truss, let's look down right here, and I can click on the bottom right here. That brings up this view right here. Actually, since we're in 3D, let's just look at it that way. And I'm going to come up to this screen and create a new sketch. And so I want to create a sketch, and it's going to again ask what plane do I want it to be on. And now I can choose one of the planes of my working surfaces right here. So I'm going to select this plane right here. Bang. Now we're looking at the bottom of the truss, and I'm going to create a 2-point rectangle. And the 2-point rectangle is going to go from a little bit inside here to a little bit inside right there. And I'm not really worried about how far it sticks out past the end. We can edit that later on. I'm also not particularly worried about where my dimensions are right here, because as I come in right here, I can change those dimensions. So remember I said we wanted 3 millimeters of MDF thickness on each side. So I can press D for the dimension key and say I want the inside of my MDF to the outside of my MDF to be 3 millimeters. And you can see everything move right there. And from the inside of my MDF to the outside of my MDF, 3 millimeters right there. So I now have this rectangle that runs the length of the truss, and I'm going to stop that sketch, bring us back into view where we can see this all together right here. And you can see that rectangle that we just drew running the entire length of our truss. And what we're going to do right now is we are going to take that stretch and we are going to extrude it. Where'd my extrude go? You can just press E for extrude, pick this surface right here, and we are going to, for our operation, we're going to tell it that we're going to cut. Instead of using this to create, we're going to use it to remove material. So we're going to do a cut, and we're going to tell it wants to know what objects to cut. So it will cut pretty much everything. We're cutting everything here, and our extent will be a distance, and we're just going to make it 150 millimeters. We want to make that happen on both sides. So make that go on two sides and 150 millimeters on both sides of that surface. There we go. You can see it breaking through there, and you can see as it goes through, it removes material from the middle. This side seems a bit ridiculously long. Let's bring that back down to 20. And this side might need to be higher later on. Let's set that up to 170 just in case. Heck, let's make it 200 just in case we make a taller truss. There we go. So that is going to cut through right there. Now, for some reason, it's only coming down this far. We need to add in additional surfaces right there and right there. It was like that rectangle didn't get made all in one piece. So there we go. We've got this whole surface coming along. And when you look at your truss now, you should be able to see 2 3mm thick pieces of MDF, separated in our case by 20 millimeters. And we're well on our way to having our 3D model made. Click on OK. Well, that's looking a lot like 2 pieces of MDF sitting right apart from each other. Now you're going to have those joined together, and you're going to have little pieces running across from this surface over to this surface right in here. And in order to create those pieces, we're going to put them right on here, here, and here, and we're going to extrude them across to the other side. So again, we come to our sketch. We're going to create a sketch right on this surface right here. And now we're going to press C for the circle button. Oh, it looks like we forgot to extrude some little piece in there. That may affect our drawing later on, but it's so tiny, I think it's going to be minor. We could always go back and edit if we had to, but press C and decide how big you want your pieces going across to be. If you're using let's say 1/2 inch dowel, that'll be 12.5 millimeters. 1/4 inch dowel is 6 millimeters. But to be nice and metric, I'm just going to put in 10 millimeters and assume you've got some nice round piece of 10 millimeter material that's going to extrude right across there. And we'll fit this in right here. And again, circle. And we'll come in right there. 10 millimeters. Press enter a second time, make sure that fixes in there. C for circle, 10 millimeters. And there we've got 3 of those coming across. Now these points right here, you might join them together with hollow members. We don't have to really do that on here, but this is going to give us a better representation, I think, of how the circle comes together, particularly down at this end. So what I'm going to do out here is we'll extrude a circle right here. And we'll go C for circle. We'll start right here. That was already 12.5 to begin with. And so I'm just going to say, let's put a 15 millimeter piece of tubing right in here. Okay, and we'll do that for the other ends as well. Let's just pan right down there. And C for circle, 15. And C for circle, 15. Okay, and now we can stop doing the sketch. So click on the stop sketch button, and we can fit the whole thing back on our screen. And let's come up here and click on that little corner there so we get to look at it in perspective a little bit. And we'll do an extrude, and we'll take that little surface right there. We want to change the direction. We should be able to extrude it in the other direction. Let's just try a distance of negative 26, not 260. That went too far. Negative 20 almost gets us all the way across. Negative 26 takes us right across. And instead of cut, we turn that to join. And now we can add some other members in right there. And these are coming across as solid. Oh, let's fit that back in. And let's tell it OK. Now that's starting to look like a truss that you might actually use in competition. There's all sorts of nice little things that you can do. If you want to get fancy, you can come in and fillet the corners, and you can certainly say that you're going to use a glue fillet around here. The fancy thing that we're going to do is we're going to apply some material properties to it. And assigning materials is done over here in your hierarchy chart. And if you come down to bodies, this is body 1. You can see a body 1 highlight when we go over top of it. And if you right click on body 1, you'll see that physical material pops up as an option right in here. And if you tell it you want to assign a physical material, you'll get a list of materials from the Fusion 360 material library. And we're going to go in and we're going to take a look at the wood materials. And you'll see that in the wood materials, there is medium density fiberboard, which is pretty close to what we're using. And so just drag that right onto there. And we should be able to see that change color a little bit. We should be able to say close. And now if we come back and right click on here, when we click on physical material, it should pop up and say MDF is in the list of materials that we're using. And when I put the mouse over top of it, you'll see that that's all assigned. There we go. We're good on that. Now, one of the neat things about doing that is that you can then come in and take a look at properties. And under properties, it will give you the mass of that structure. And so that was a right click on body 1. And it tells me that my mass is 45.8 grams because I'm using medium density fiberboard. It goes through and it calculates the volume, multiplies by the density of MDF, and it predicts the mass. And that'll be a fairly accurate mass prediction. In fact, last year's winning truss was at 41 grams. The second place truss was at 48. And this year so far, I've seen some trusses coming in around 50. And they have some more material to them than this one does. Keep in mind that this is also modeling our joining points as MDF, and we've modeled them as solid. So if you're using a lighter material to join your nodes together, or you've made smaller nodes, then that'll be a little bit lighter. But on the other hand, if you've used glue in there and the glue hasn't dried up, that's not accounted for in this model either. So any glue fillets or that you might have in there would add to the mass of your truss. But there you go. You now have a beautiful MDF truss. It weighs 45 grams. And if you've got a fancy 3D mouse, you can spin it around and take a look at it from all these nifty angles. That in itself is kind of a cool feature. But how do we test it? Now, before we go and test it, remember I said things were parametric? This is really cool. Our sketches still exist in here. So if we click on the little down arrow next to sketches and come over here, we can go in here and we can go back. Sketch 1 was the first sketch that we did. And we can right click on there and there's an option to edit that sketch. And now all of those nodes that we created right in here, let's say I just want to bump the height of this truss up a little bit. So I've got more of my forces going in the vertical plane. I'm going to go 130 millimeters right in there. That lifts that node up there. Makes this one a little bit longer, but anyways, I can stop my sketch. And now my truss has extended in height up to 130 millimeters right here. So that's also kind of cool. Now the downside of making that a little bit bigger is if I come back to body one and go right click, we were at 45 grams before. Let's come down to properties, and now we're at 46 grams. So we added a gram of material by making that a little bit taller. Not nearly as much as I'd expected, actually. If we wanted to shave weight off of this structure, we might be able to come in here and take a look at some of these nodes and say those nodes are looking ridiculously huge. Let's go back to sketch one, and we will edit that sketch. And we told them that they were 20 millimeters in diameter. Zoom in on that, double click on it. Let's take them down to 15. And there are ways you can make this even more parametric so that you only need to change one number, but I can only fit so much into. Yeah, let's carefully choose the correct dimension right there. Bring that down to 15 and stop sketch. And here we are. You can see that those nodes have shrunk down a little bit, and our properties now on this body, we come in here, right click, get the properties. We've now shrunk the mass down to 44.8. So we've got more of our material now doing useful things rather than sitting around being useless nodes. And let's click OK. Always a good idea to save these things now because you're using a cloud-enabled environment. Fusion 360 does a good job of saving this while you go along, but it never hurts to give it a name and tell it you want to save that. And you've got a number of different places where you can save it on the cloud. So you can click on the down arrow right here. And I've been saving this in a folder called Truss Analysis, and I'm going to save this one as Truss 3. You might have to create a new folder to hold these things in, but the options are all right there. This won't be on your hard drive. There is a way to download some of this onto your hard drive, but for right now you're storing it on the cloud. I'm not really fond of that, but AutoCAD's giving us the software for free, so that's kind of cool. We'll let them store it on their cloud. Okay, now the exciting part. You've been waiting for this. Let's go from here. We're in our modeling mode right now. So in the top left corner of the screen, you can come down to the simulation mode. And the simulation workspace lets us assign loads and fixed loads and all that. And we're going to start off by doing static stress. You see there's a number of different analysis that you can do on here. Some of them are very cool. Vent simulation, you can fire high velocity particles into sheets of ductile material and watch how they deform. We're just going to go with static stress to begin with. And then later on, we're going to take a look at structural buckling. But you need to do static stress to make sure nothing else is falling apart. And so we select static stress and we go create study. Okay, so there's our truss. Nothing looks too different except now over here under static stress, we have something called load case 1, and we've got some new icons along the top of the screen. And so what we need to do is we need to provide a load and we need to provide some constraints. Let's start off with the load because we know where the load's going to go and we made a special spot for it. And so we're going to create a structural load and zoom in on that little flat spot that we put in right there and tell it that we are putting a 20 Newton load going down right in there. And let's hope that when you put your load in there, it's perfectly symmetrical and perfectly in the middle because that's how we're simulating this. The next thing we need to do is we need to provide some constraints. And these two out here are going to be being held in place by the steel rods that you push right through there. And so what we need to do is come up with some constraints. And we are going to have structural constraints. So just click on C. And right in the middle right there, we are going to tell it that that is going to be a pin connector, and that entire face is going to be pinned in place, and it's going to be free to rotate tangentially, but it's going to be fixed in the axial and radial dimensions. In other words, it can't slide that way, that's axial, and it can't slide radially up and down or forwards and backwards. Not entirely true, but it doesn't give me the option to hold it right in there, but it can flow tangentially, so it can rotate. And we'll say OK. And then we'll also create a constraint on this surface right here. And again, we'll pin that surface in place, and we'll allow that one to rotate. Because I've got these two fixed as pins, it's not exactly what we're doing, but it's close enough that we'll be able to get most of the analysis working. Okay, so we've got it fixed in two places. We've got a load out here. Under solve, do a pre-check on here. Study setup has all the information required. And now we go ahead and we tell it we want it to solve. And it goes out there on the cloud, and we tell it solve one study. And so all of our design right now is being uploaded onto Autodesk servers, and they're processing the static stress analysis. And this is just going to take a minute or two to do. You can actually do it quicker on your own computer, but what's nice about having AutoCAD handle it is that even low spec computers are going to be able to perform fairly complex analysis. And there we go. I'm going to close that right now. And here is our results. And what you'll see right here is down in this window right here, it shows you the safety factor that it's calculating. And for this truss, it's come up with a warning that our minimum safety factor is 1.52. And technically, a safety factor over 1 means it should not break. Should. You've got to remember that AutoCAD is, or sorry, Fusion 360 is assuming that the material is all perfect, that there's no surface imperfections, that there was no warping that occurred in the MDF while it was sitting around, that the MDF is perfectly uniform, and essentially it's in this tidy little mathematically perfect world. And so we're getting a safety factor of 1.52 in these yellow regions right in here. And some of this material is very safe down here because we fixed both these nodes. There's actually no force going back and forth, and they're not entirely true in the way we're going to be loading it in real life. But you can see that our safety factor in our vertical columns tells us that they are not likely to fail in pure compressive stress. We're going to that doesn't include buckling. Buckling gets a little bit more complex, and we are going to do a buckling analysis. But right here, it looks like our most hazardous parts of this structure are these narrow lines right here, and we get our safety factor down as low as 1.52, and you can see it warning us right there that something is likely to perhaps break in there. So maybe we want to come back and thicken those up a little bit before we go on to ask about buckling. So using this design, you can see it's going to deform downwards. Top is going to be in tension and bottom is going to be in compression. Our stress in the top members is higher than in the bottom members because it's carrying both a horizontal and a vertical component of force, and because we've made these very narrow. Our zero force members right in here, they're just doing their job and keeping these two parts kind of apart and keeping this node from wandering all over the place. They're not really carrying a lot of force, so they have a very high safety factor. Let's go back to our model and let's add some extra material into our tensile members and see if we can bring that safety factor up a little bit. I'm going to click on the close button right here, and I'm going to leave the simulation environment and come back to the model environment. And there's our model again. And it was these members in right here along the top that we wanted to increase their thickness a little bit. Those are contained in sketch 1. So we go back to good old sketch 1, edit sketch, and there's the dimensions right in there. And I'm going to move that up to 2. And I'm going to move this one up to 2. And then I'll come over here. And I'm going to move that up to 2. Move that up to 2. And that's doubling my cross-sectional area right in there. So that should give me twice the safety factor. Going to move this up to 3 and move that up to 3. Those are tensile, purely in tension, so that'll make it a bit stronger. I'm going to stop that sketch. Now you can see we've got beefed up members running right across there. We can query the properties to find out what that did to our mass. We're now up at 50 grams, and that's okay with me. Well, we'd like to get it down lower, but we've got a few more analysis to do on here. And let's come back to our simulation environment now. And we've changed some things on here, so we have to resolve this problem. So again, we click on the solve button and tell it to solve one study. And it will do that because we have changed things. If you haven't changed anything, it won't run the simulation for you again because there'd be no point. Okay, the analysis is finished. I can close that window. And now it's identified a minimum safety factor out here somewhere. And that, I'm guessing, is likely to be a glitch in the drawing. But what's really nice right here is that the top members are all in green. And let's see if we can zoom in right here, see where it says that. Yeah, right down inside here it says that's our safety factor in there. You could clean that up by doing a little bit of a fillet. That's probably an artifact of the solving process. The way this solving is taking place is using something called finite element analysis, which is a big word until you break it down into the individual words and realize finite means a fixed number of things, element means parts, and analysis means doing the math. So it breaks it down into a fixed number of parts, and then it does the math on each one of the individual parts. It would be really hard to do by hand, but computers like doing math, so they do a great job of it. If you come to display, you can turn on the mesh view. And in the mesh view, you can see the mesh that was being created, and we have this tiny little node right in here. And that's where it's seeing the flaw. So when it does its analysis, you can take a look in here and see how it's all meshed. And people who are experts in finite element analysis would kind of be scoffing at us for just using the default setup. They'd point out ways that the mesh could be optimized to solve the problem more elegantly. But we already know that we could solve the problem a lot more quickly just by taking a look at it as a truss. We wanted to get pretty pictures and take a look at the things that we can do in Fusion 360. So anyways, there's your mesh view, and you can see how the computer has gone through and broken the truss down into all of these members. The actual meshing at one time would have required somebody with a PhD in engineering and computer science to figure all that out. Up until a couple of decades ago, developing the mesh was one of the most complex parts of doing finite element analysis. And for high-end analysis, it still is. Let's go back here and change our views. Where were we? Right here. Views. Oh, display. Change that back to our results view. And there we go. We can see that we've dealt with our stresses in the top members. And these bottom members are not likely to fail in pure compressive stress. What we want to find out now is, are they likely to fail in buckling? Now, to do that, we're going to have to come in and create a new study because this is actually a fairly simple analysis. and I realize what I'm saying when I'm saying that. We're using more computer power here than was probably available to anyone at the time I was studying to become a tech ed teacher. Certainly more sophisticated analysis than was available to anyone short of about graduate level engineering work. But now the software has been developed so that it's reasonably easy to use and visualize. So we're going to create a new study, click on the study button, and we're going to take a look at structural buckling. And we're going to create a study right here. And just like we did before, we're going to have to apply some constraints. And we'll put a pinned constraint right here. And notice that we highlighted the entire inside right there. And we'll put a pinned constraint right there. So those two surfaces are pinned. And then we will create a load, a structural load. And we're going to create that on this surface right here, pointing downwards. And we'll say that's going to be 20 newtons. All right, off to the cloud. Now, if you're a commercial user of Fusion 360, Autodesk charges you cloud credits for solving these problems, and each of the linear static stresses is the ones that we just did is 5 credits, and a solution like this would be about 15 credits, and a credit is roughly $1. So far today, we've probably churned through $40 or $50 worth of work Autodesk server that we'd have to pay out if we were a commercial client. And Autodesk provides that to students because they want you to be able to use the software, learn how to, use their software, show it to your students in the future. But at the same time, we get to find out really cool things as we take a look at this. And now we see that the buckling has come up with a more complex analysis. Now, this is where it's important for you to understand a little bit about what's going on because we know that we should not be seeing buckling in these top members because they should be in tension. Makes sense that we see it down here in the bottom, but we shouldn't see it in the top. Yet that's what Autodesk shows us. And that's because there's different buckling modes that it warns us about. And in buckling mode 1, our results right here show a negative value. And what that means is that it's warning us that if this load were reversed and it was pushed up this way, that we would have buckling right in here. What we want to do is change our buckling mode to find the positive mode right in here. So of the 3 modes that it analyzed, click on the positive mode, and this is what we're actually likely to see. And you can see that with this design right here, we've got buckling occurring right in here. We put that load down there. We get a compressive stress occurring on the bottom. And these nodes right here are a little bit too long and they pop out to the side. We're getting pretty close, but let's go back to our model environment. And let's take a look at sketch 1. And we're going to edit sketch 1 up again to see what could we do about buckling in there. Well, one thing that we could do about buckling is we could increase the thickness of these bottom members to make them a little more rigid. The other reason that we're getting buckling in there is because the horizontal force in this member right here is fairly high. So we could increase the height of this member right here from 130. Let's set that up to 150. And now our force is being pulled in a nice straight line right up here. And because we've got a higher angle right here, the relationship of our vertical force, which is fixed to our horizontal force, is going to change, and we're going to have less horizontal force coming across right in here. So we can stop that sketch, and you can see the changes have happened right in here. Again, we've got a little bit of a glitch in our extrude right there. We could come back and fix that. And if it's causing problems with our analysis, we will come back and fix it. I'm not going to worry about it for right now. Let's go back to simulation mode and let's solve our structural buckling and see what happens now with less horizontal force being pulled in the bottom member. There we go. The results are done, and we click on close, and we've still buckled right in there. Although, let's take a look right here. Yeah, we're at 0.744 times load, and our maximum buckling force is right in here. We want to brace that up just a little bit more. We want to get this number right here, like I say, up above 1 so that it's stiff. Did I say less than 1? I meant more than 1. Right now, the 0.744 times load, we've got a 20 Newton load on it. That means that it predicts this structure is going to buckle at 0.74 times 20 newtons. So at about 15 newtons, this structure is likely going to buckle. So I think we are going to have to thicken up our bottom members right here, see if we can put a bit more meat on them and stiffen them up that way. So back to the model environment and into sketch 1, and you can see why all that time spent setting up the parametric sketch was so helpful, because we just come in here to edit parametric sketch, and we change this up to 4, change that to 4, and that stiffens up the bottom quite nicely right there. And let's stop that sketch. There we go. We've added some meat to this structure. So let's just take a look in here at our properties, and it now tells us we're up to 55 grams. We're not going to be winning the competition with this truss, but it is also a very simple truss. The truss that won last year was a little bit more complex, had many more members right down here, and you're welcome to go through and design all that. Let's come back into simulation, and let's solve this again. Gonna close that right there. Now, again, this is important why you need to know what results to expect, because there's no way we should see buckling in a tensile member. And you'll see that buckling mode 2 has changed right here. We want to check, and this is giving us all negative buckling factors. What that means is that if we reverse the direction, those ones, and we reverse the load, those ones are going to buckle. I don't see any positive buckling load factors in here. So I think we've stiffened this structure up to the point where it should survive. Because we could do different buckling modes and let the computer figure all that out. But I think we've got this structure pretty rigid. And let's take a look at our linear static stress analysis. And we can do a static stress on it as well. And let's close that. And we're still looking at load case 1 for structural buckling. To see our static stress, we need to activate the static stress model. And again, this looks like we should be seeing, you can see it's giving us this warning that our safety factor is up to 2.41. I can live with 2.41 as a safety factor, considering that there's no human life involved here. You can see that the stress does increase right down here a little bit, but by and large, these members that were appearing totally unstressed in static stress were at risk of buckling until we thicken them up. These ones right up here, they're going to be loaded in tensile stress. This one right in here, you can see coming up and down, is fairly heavily stressed. but nothing's showing up as stressed in these zero force members in the middle. So I'm just going to make a few tweaks to see if we can get our weight down a little bit, and then let's see how light we can make this, and then I'm going to be done. So back to our simulation, and let's come back into modeling and sketch one. And let's come in here and let's edit that sketch. We've still got more material in here than we need. Let's take this down to 10 millimeters. Actually, let's make it 11 because we've got a 10 millimeter pin joining those together. We don't want to go smaller than that. That would look awkward. You could do it, but 11. And 11. And what else can we do to bring this down? Let's see what happens if we bring this down a little bit to 130, but shift it out a little bit to 180. Maybe 190. There we go. That keeps that pretty lined up in there. Wonder what happens if we take these down to 3.5. Now, I'm keeping everything symmetric. Technically, there's no reason why they need to be perfectly symmetric. This one back here can probably come down. Now, in our simulation, we don't show any loads in there because the way I've pinned the constraints in here, that's maybe a bit egregious. Now, these ones are sitting at 1 millimeter by 1 millimeter. We could take them down smaller, but the laser probably won't cut much thinner than that. You've got to remember the laser has about a 0.5 millimeter kerf, so everything the laser cuts comes out slightly smaller than what you see on here. So let's see, let's stop that sketch. There's a couple of ways to get your drawing out of Fusion 360 and onto the laser. Probably the easiest is to take sketch one and right click on it and just go save as DXF. And you can save that on your hard drive somewhere. I've saved mine as truss3.dxf, and you can save it right there. And then you can take AutoCAD and just open up Truss 3, and there you should have a 1-to-1 scale drawing of your truss, and you'll have to come in and trim up all the corners and all that to get the final output, but the cool thing is you know it's probably going to work. Keep in mind that what we've predicted here is a prediction, and your materials may vary. Something as simple as the fact is that when the laser cuts these narrow members, the laser cuts along this line, and the laser has finite width. The kerf on the laser is about 0.5 millimeters in diameter where it cuts through. So your members are going to come through slightly narrower. And, again, your material may be slightly different and definitely less perfect than the mathematically perfect material used in the calculations in Fusion 360. So simulation is a great way to help design products, but you still have to do testing and you still have to be able to understand and interpret the results to get the most value out of simulation. So there you have it, how to design your truss in the computer. Don't forget to test it, and do expect to see things behave just a little differently than you expect.